This chart represents quarks, which are among the fundamental building blocks of the Standard Model. Quarks come in 6 different flavors. These flavors are grouped into 3 generations, with each new generation being heavier and much less stable than the previous one. The heavier quarks exist only for an incredibly short time before decaying into lighter particles. One of the most fascinating things about quarks is that they carry fractional electric charge, unlike every particle you usually encounter, whose charge is either +1 or -1. Quarks have charges of only +2/3 or -1/3 of the elementary charge. Up, charm, and top quarks each have a charge of +2/3, while down, strange, and bottom quarks each carry -1/3. This explains the charges of the particles we observe. For example, a proton consists of 2 up quarks and 1 down quark. Adding their charges gives +1. A neutron contains 1 up quark and 2 down quarks, which equals to 0. But electric charge isn't the only charge quarks possess. They also carry something unique called color charge, which has nothing to do with actual colors. It is simply the name physicists give to the charge associated with the strong nuclear force. There are 3 possible color charges: red, green, and blue. The strong force is carried by particles called gluons, which constantly exchange color between quarks. This continuous exchange binds quarks together so strongly that they cannot escape from one another. This leads to one of the most remarkable properties of nature called color confinement. Imagine trying to pull 2 quarks apart. Unlike gravity or electromagnetism, where the force becomes weaker as objects move farther apart, the strong force actually becomes stronger. The energy stored between the quarks keeps increasing, almost like stretching an infinitely strong rubber band. Eventually, instead of separating the quarks, nature converts that stored energy into a brand new quark and antiquark pair through Einstein's equation. So, rather than finding a free quark, you simply end up with 2 new particles. This is why no isolated quark has ever been observed experimentally. Surprisingly, the opposite happens when quarks are extremely close together. At very small distances, the strong force becomes weak, allowing quarks to move almost freely inside protons and neutrons. This phenomenon is called asymptotic freedom, and it was one of the key discoveries that led to our modern theory of the strong interaction known as quantum chromodynamics. Finally, quarks are also spin 1/2 fermions, meaning they obey the Pauli exclusion principle. And every quark has a corresponding antiquark with the same mass and spin, but opposite electric charge, opposite color charge, and opposite baryon number. Together, quarks combine in groups of 3 to form baryons, like protons and neutrons, or as a quark-antiquark pair to form mesons. So, although quarks can never exist freely, they are the invisible building blocks that give rise to nearly all the ordinary matter in our universe.